Welcome to The Explainer. Today we're jumping into dynamic balancing, a process that's absolutely crucial in high-precision manufacturing. It affects everything from the washing machine in your laundry room to a massive jet engine. And in those machines, even a tiny unbalance spinning at high speed can create destructive forces hundreds of times its own weight. It's a huge deal.
So let's kick things off with a question that honestly seems pretty logical. On the surface, it makes perfect sense, right? But it's actually a trap, and it hides a really critical engineering truth. We're going to break down exactly why thinking this way can lead to some major, and I mean very expensive problems down the line.
Okay, so let's get right into it by looking at the very first essential stage. This is all about getting the individual parts right, long before they're ever put together.
What are we talking about here? Well, this process focuses on just one single component at a time. Think of a motor rotor, maybe a fan impeller, or even a simple drive shaft. The whole goal is to hunt down and eliminate these tiny little flaws that might come from the material itself or from the machining process. You're trying to get each and every piece as close to perfect as you can, right from the very start.
And the benefits of doing it this way? Well, they're all about being smart and efficient, You're tackling the problem right at the source when it's just plain easier and cheaper to fix. The part is out in the open, so you can set up high-speed, automated corrections for huge batches of them. But maybe most importantly, you're protecting all the other delicate parts, like precision bearings, from getting damaged later on by a component that wasn't balanced properly from the get-go.
All right, so we've got our perfectly balanced components. Now what? Let's move on to the next phase and see how it all builds on that first step. Now, this isn't about redoing the work we just did. Think of this as the final polish on the entire complete system. See, this is where it gets really interesting. This step is designed to fix brand new, super subtle imbalances that were actually created when you put everything together. We're talking about tiny gaps, maybe some uneven fastening, or just the way all the parts fit together. There's even a term for it: assembly tolerance stack-up. So you're basically balancing the whole machine exactly as it's going to run in the real world. So here's the crucial point. This stage isn't redundant at all. It's correcting a completely different kind of problem. This is the only way you can get the absolute highest accuracy because it takes into account how all the parts are actually interacting with each other. But, and this is a big but, making corrections at this stage is way, way harder. I mean, you can imagine with a complex machine, everything's already sealed up, so just getting access is a huge challenge.
And this table just lays it all out perfectly. Look at the timing, the correction methods. You go from having lots of options to being very limited. And most importantly, check out the source of the unbalance they're each designed to fix. One is foundational, focused on the raw part. The other is systemic, focused on the final assembled machine. They really are two totally different jobs for two totally different problems.
Which, brings us right back to that big question we started with. If we're going to do this super careful final check anyway, why can't we just skip that first step? Save a little time, save a little money. Well, the answer really boils down to two huge risks that can absolutely stop a production line cold. First, if a part is really unbalanced, it can generate so much force that it literally destroys expensive, high-precision bearings on the very first test run. And second, the final assembly only has so much room for adding little correction weights. If the error from that initial component is too big, you might physically run out of ways to fix it at the end. You're just stuck. And to really get why this is so critical, you've got to think about it a little differently. It's not just simple addition. It's all about vector math. We're talking about forces and the different directions they're pushing in. So the total unbalance isn't just one error plus another. It's the sum of these two force vectors. You've got the force from the component unbalance pushing one way and the force from the assembly errors pushing another. Now, if that first vector, the component unbalance, is already huge, it makes the final total way larger and potentially just impossible to counteract with the small, precise fixes you can make at the end. You're starting in a hole that's too deep to climb out of. So, at the end of the day, the professional approach, the smart approach, it isn't an either-or choice. It's a both-and strategy. To get high performance and real reliability, you absolutely need to do both. Think of it this way. Component balancing is like making sure every single brick you're building with is solid and perfectly formed. It's quality control at the most basic, fundamental level. And then finished product balancing. That's like checking the final wall after all the bricks and mortar are in place. You're making sure the entire structure, the whole system, is perfectly straight and true. It's that final check for total integrity.
So the crucial takeaway here is this two-stage strategy. It's simple, really. Step 1, do detailed balancing on the individual parts. Get them right. Step 2, after everything is assembled, do a final balance check on the whole system at its real operational speed. That's it. It's the only proven way to guarantee the highest levels of precision, safety, and reliability in modern machines.
And we'll leave you with this question to think about. It really highlights why this whole two-step process isn't just some best practice. It's absolutely essential. At those kinds of speeds, even a tiny error generates an immense, destructive force. It's not just about making things run smoothly, it's about preventing a catastrophic failure. Thanks for joining us.